talk. Thank you so much for the fantastic talk. We're a little pressed on time, so we're gonna move on to the next one. But everyone, great. And so next up is Ludovic Salomon. I think I've hopefully pronounced that right. Who is going to be talking about multi-objective optimization with CVXPY and MOCVXPY.
Okay, everyone can hear me and everyone can see my screen? Suppose?
Yes.
Great, perfect. So in this case, good afternoon, everyone, and well, welcome to this talk. In this talk, I will present MOCVXPY, a CVXPY extension for multi-objective optimization. This is a joint work, well, it was a work when I was a postdoc at Polytechnique Montréal, and it was a joint work with the University of Vienna, with Professor Dorfler and Professor Lone. Okay, well, for those who may not be familiar with multi-objective optimization, this is a generalization of single-objective optimization. So you just, that exactly almost the same framework. We need to optimize a function over a set of constraints, and but contrary to single objective optimization, the objective function is composed of several components and not only one. And this poses a major challenge, which is the following: how do we compare one solution with another? Indeed, in single objective optimization, what you do, you just take the objective value of your function, it is a scalar value, and you can easily compare one solution with another. In multi-objective optimization, this is not the case anymore, and in this case, what we do, we use what we call the natural ordering, which is just the following. You take the objective function, objective component of your first solution, the objective component of your second solution, and if all the objective components of your first solution are better than all the objective components of your second solution, in this case, we say that one solution is better than another. And on the right, you can see that I just made a short illustration. You can see that in this case, we can x1 is better than x2 because all objective components of x1 are better than all objective components of x2. In this case, with this natural ordering, what we can do, we can now define what is an optimal solution for multi-objective optimization, which is just the following. It is exactly the same as in single objective optimization. In single objective optimization, an optimal solution is a solution for which there does not exist any point that is better than another. But not if you take a look at on the right, on the top right, we can see that there is some zone on each part of the fx2 function, fx2 values that well that cannot be that we cannot use to compare solution between each other. And due to this incomparability relation, most of the time in multi-objective optimization, the set of all solutions is not a singleton, but is composed of several different solutions, what we call the Pareto set. And what is really important in multi-objective optimization is the image of the Pareto set by the objective function, what we call the Pareto front. Why is the Pareto front important? It is important because it represents the best trade-offs that one can get faced with this problem. And I'll show you some, in the case of derivative minimization problem, I can show you some Pareto fronts that are the following, and that are represented in red. So now imagine I am a user and I want to find a solver to solve my multi-objective optimization problem. What can I use? First thing, if you type on the internet, I will bet you that most of the time the first thing that will appear are evolutionary algorithms. In this case, what we can see, I just list some of them, and I'm sure that there exist many, and most of the time they work the following. They just try to evolve a population of points that will, by sampling, crossover, mutation, and you can hope that at the end it will get a good representation of the Pareto front. Problems, these evolutionary algorithms are heuristics, and most of the time, I hope that you have a bit of structure on your problem. I mean, in single objective optimization, I hope that most of you will not use, for example, to solve linear problems, an evolutionary solver because there exist more efficient algorithms in this case. So if we take now at exact computational libraries, the situation is a bit dire. For example, for MOLP, the situation is not too bad because there exist some linear solvers for multiobjective optimization, belt solve, inner, or if you want to solve a mixed integer linear problem, polyskip. If now we move to the next step, so multiobjective nonlinear optimization, there exists some small implementation of new algorithms, but most of the time are extremely recent. And the thing that you can try to use them, but for each solver, be it linear solver or nonlinear solvers, you have to enter the problem in some format. It's not always intuitive. Can also be prone to declaration errors. For example, some of these solvers are built on Pyomo or MATLAB, and you need the explicit formulation of the gradient or UHN to speed up the resolution. Which comes back to a last library that is the only one that tried to be built on some kind of intuitive format for users, which is multi-objective optimization, multi-objective algorithm, which is built on top of Jump. But still, to have several libraries should not be so bad. That is why I will introduce now MOCVXPY, which is a CVXPY extension for multi-objective optimization. MOCVXPY targets a smaller set of multi-objective problems. In this case, we need our problem to be convex. We need our decision. We need our decision set to be also convex, and naturally, we are still using the natural ordering relation. With that, we still have some advantages. First one, it is built on top of CVXPY, so we can reuse the same grammar as the one that is used by CVXPY. It also directly benefits from computational advances made in CVXPY. As an anecdote, last week I was just trying to move from one version of CVXPY to the most recent one, and I saw some improvement on my benchmark. So that's a nice feature. And a last thing is that in the case of convex problems, we have something that is quite interesting. We are able to compute a numerical approximation that is guaranteed to be able to enclose in some sort of way the Pareto front of your problem. Important, if your problem is not convex, please try to use other solvers. So just as a remember, you are all familiar on how you use CVXPY. So classical one, you take some variables, you define your objective and your constraint using some CVXPY axioms. You define a problem, call the solve method, and then boom, you get your optimal decision values if everything goes well. For MOCVXPY, it's almost the same. So we just this time add MOCVXPY as a dependent. Define MOCP variable, which is just an unclosed CVXPY variable object. We define a MOCVXPY problem, exactly the same methods, and in this case, we have not only a set of not only one solution, but most of the time a set of solutions with the values field. So with the value seed, you can do exactly the same as for the value for CVXPY to get access to all the values of your optimal solution of your problems. And naturally, as for CVXPY, it's integrated with the whole Python ecosystem. And as you can see, this is the solution that we obtain on this problem. Just before moving to the application, I just want to do a quick reminder of what are the algorithms behind MOCVXPY. The idea behind all these algorithms is to enclose the Pareto front even either by polyhedral inner or outer approximation, which are in the convex case, or by enclosure, which is just a set of boxes that enclose the Pareto, the current Pareto front approximation. And along the iteration, this enclosure will be refined, and after the distance between one inner approximation and one outer approximation is reached, we just stop the algorithms. MOCVXPY implements three algorithms, two Benson times method and one enclosure-based algorithm. they are adaptive scalarization-based approaches, which mean that they need to solve a succession of single objective parameterized problems, which are all based on CVXPY. And solvers used to solve the single objective problems are customizable. So for example, to solve a solver that's exactly the same way as for CVXPY, and if you want to be able to customize the subsolver for your problem, you can still precise the scalarization solver option. Now, before concluding, I just want to give you a short example of what is a nice application for multi-objective convex optimization. So it's really nice because Professor Diamond, I just explained the problem before, so I will not repeat it myself. The idea is just to try to design an electric network so that you minimize the generation cost and the power losses in the network. And in this case, we have several objectives and not only one, but we try to minimize at the same time. So this is the whole description of the problem, but the equations that are a bit nasty are the power flow equations, which are non-convex. So what we do first, in the first time, we just reformulate them, and then remove the rank 1 constraint so that we have a convex realization of the problem. In this case, we solve the problem using MOCVXPY, and among the solutions, using some kind of post-processing tricks, we are able to collect the ones that are exact. And you can see that in this case, we are able, with our problems, to get the part of the Pareto front for a small electric network. So, as a conclusion, MOCVXPY is an extension of CVXPY for multi-objective convex optimization. As for CVXPY, it allows to intuitively model the problem and solve it with 3 state-of-the-art algorithms. I didn't mention every kind of feature that it has, so I invite you to read the paper. So it has also basic parallelism, and we can order more general ordering cone than the natural ordering. So I'm really happy for this package, but not everything is perfect. The documentation is incomplete. It is not yet available on PyPy, and I will try to make it available soon. And also, and I really invite you to help me for that, we need more tests and real-world examples that fit into this framework because it allows us to see which one is better if our algorithms are robust and efficient for all your applications. For future works, we want to tackle mixed-integer multi-objective convex optimization, try to integrate for some special kind of problems with state-of-the-art solvers that will be more efficient than our generic solvers. And a last thing, but I'm alone of this one, to try to follow CVXPY's evolution. So, for example, to introduce DPP rules, DNLP rules, and many other features. I thank you for your attention. Do you have any question?
Thank you so much. Sadly, we are behind schedule a little bit, so I will suggest that people who have questions hop on Zoom and type them in the chat, and hopefully we'll be able to get the questions answered.